Today, we're talking about right triangles. I want to continue the PowerPoint we started yesterday. Now I know this seems weird if you were gone yesterday. We jumped to chapter 8 all of a sudden. You're in chapter 4, which we still are. But we're jumping to chapter 8 because I want to finish a couple of properties about right triangles. I didn't like the way that the book just like stopped talking about right triangles in the middle of chapter 4, and then it came up later for like 3 sections. So for the next couple of days, remember, we're going to be talking about a little bit of sections out of chapter 8 through about the middle of next week-ish, so about a week now. Do a couple sections. Pretty easy. We'll learn a couple formulas, and we're going to learn how to use them. All right. Questions on what we're doing? Perfect. All right, here we go. Goals today. I want to do a quick review of that one postulate we had yesterday. That was the AA postulate 7.1. I want to review it today. I want to make sure that we know how it works. And because we need it, this one's actually required before we get to our first theorem today. Okay? So that's what I want to make sure of. Now, new stuff today. New stuff. I want to talk about radicals and roots today. I want to talk about what they are, what all the vocab terms are for them. There's a ton of words that go with radicals and roots. And then that'll lead us into our first theorem today. Now the theorem today is actually just proved because of this one. So if you know this postulate, it's like a one-step proof. It automatically works. There's a couple other steps through to a flung proof. There's a couple other things we had to talk about. But this is our first theorem. This is the one theorem I want to get today. And then we'll venture into our new stuff tomorrow, and we'll see the actual formulas we need. But today, this will probably be the most challenging part. I'm hoping that you've seen this before in junior high, but I can't guarantee it. So that's why I always introduce it very light today, and then we start kind of going into it slowly. Some people definitely need to see this. This is the part that I said we'll need calculators. Okay, that's why I've been so adamant about getting mine back. So we'll definitely. I'm going to show you how to do this stuff by hand. Not directly related to the calculator idea, but it's important that you know how to do these by hand because it's actually faster. If I teach you the shortcuts for this, it's quicker than somebody using a calculator, and it'll give you a better answer. So that's what we're going to talk about. Homework today. That's the homework that I give you. That was at page 278, 289. That's due tomorrow. Remember that. It's due tomorrow, February 1st. That's the 4 proofs, and then the stuff about finding the walls and parts that are equal and all that good stuff, or finding the value of x and y on the problem. That's due tomorrow. Remember, on the proofs of that homework, the proofs, I think it's the first 4 problems, you are allowed to do flowchart proofs. You don't have to do full statement of reasons, or the book says paragraph proofs. You don't have to do that. You can do flowcharts, because that's still a style of proof. Okay. Questions about what our homework is? Okay. I think most people had it. You had a pretty good start on it yesterday. Just make sure it's due tomorrow. Don't forget that. Okay, let's jump right in. This is the first postulate. This is the stuff we had yesterday. You should already have this one down unless you weren't taking notes yesterday. So here you go. 2 angles of one triangle are equal to 2 angles of another triangle. Then the triangles are similar. Okay, this one talks about if you're given 2 triangles, okay, like what I have here, and they have 2 angles marked, the triangles are quote-unquote similar. Now the definition of similar means that they're proportional. So like, let's say you had a picture of this one on your phone, this one right here, and you pinched and zoomed on it. Now the picture has changed. It's went bigger or smaller depending on which direction you did for the pinch and zoom. It's now a different picture, but they're similar. They look like the same picture. It just got bigger. That's the idea. It does degrade quality of photos when you do that. Because when you pinch and zoom, and you zoom in on an object, you'll start to notice the pixels.
Why can't it like repixel?
It does it for a while. It does. They have a smart haptic engine on the inside that it actually does fill in certain pixels. So it does look good for a while, and then it loses it. Because after you start filling in pixels, those pixels aren't perfect. They're just like color shaded correctly for a while. Then after a while, you'll notice that they get all blurry and stuff because it's color corrected so many times that it can't figure out what color is actually supposed to be there anymore, and it loses it. So it's impressive what those cameras can do. It's filling in a lot of stuff when you pinch and zoom, and it does it on the fly. That's why that first iPhone that came out in 2007 was so impressive, because it could do this. I'm not even joking. It could do that property better than any other phone on the market, and it was unrivaled for a while until Android came out, and then they started competing a little more. But yeah, it could do that. It had almost a small form of artificial intelligence where it could fill in dots.
What's better right now, Apple or Samsung?
That's a debate. I could argue both ways. So I know that seems weird, but I could argue both. But all right. But this is the first one. Now the word similar, remember, means proportional. So if I had the length of one of these walls, you could multiply it by a number, and it would change it into the other walls because there exists one number that can make it that way. And again, what we're going to try to learn in the next couple days is how can you find that number like this stuff. Now, the notation for similarity is the little squiggly sign. We talked about that yesterday. Now, this is the one postulate we need. We need this one to get to our first theorem today to understand why it works. So if you read it again, if two angles are given from two different pictures, then the pictures are automatically similar. They're automatically proportional because the angles in the corners work. Now, this one really mimics that third angle theorem we had in the beginning of chapter 4. Two angles match from one triangle to another, their third angles have to match. Well, I don't need that. I just want to talk about that they are similar. They're scales of each other. All right. So let's get to the new stuff today. Radicals, here you go. We're going to do this pretty quick. I'm only going to do a few examples of this. I'm not going to go very far in depth on this one, just because the goal today is just to intro them. I don't want to go in depth and confuse you, and hopefully today's like the first day you get to learn vocabulary terms. So here's the words I want to talk about. So on radicals or roots. Roots, also known as square roots or cube roots, those specific names, square roots or cube roots, those are types of radicals. Okay, square roots and cube roots. They are all the same type of math. They have different answers. There's other types of roots. These are probably the most famous ones that people know of. There's quartic roots, and they keep going. Okay, there is more types of roots. The goal today is to intro what those are. Because some people have never seen that before. They've never seen the word. They don't even know what it looks like or how to do it. Some people are familiar with it. You have those buttons on your calculator. Okay, those are things we're going to look at today. Now, we're not going to look at the calculator today. We'll look at that tomorrow. So if you have a personal calculator at home, you will want to bring it tomorrow because I'll show you how to use it correctly. That's kind of the goal of one of the things we're going to do tomorrow. Question? Yes, you may. All right, but so we're talking about roots. Now, vocab terms that are only dealing with these. Okay, and this is, by the way, this is a root. This is actually a square root. Okay, that's a square root. Now, it kind of looks like a long division sign, but it has a tail. It has a tail up front. Okay. There is terms that go with these. So the words we're going to start learning. We're going to learn what a radical sign is, what a radicand is, and what the actual index number is. These are the three main words of any type of radical or any type of root. So let me give you a picture here. So I'm going to get rid of this one, and I'll actually show you an example where they fill in numbers here instead of giving me like an X in this case. So here's my example. And it actually has all the words written on it. So they have the radical sign. The radical symbol or radical sign is the actual like house with a little tail out front. That's called a radical sign. We don't call them square root signs. It's a radical sign. The number out front, and now this is the way that Microsoft Word did it. They make the number outside really, really big. I've seen them where they're tiny. I've seen them where they're written down here in the little tail of the radical sign. This number is called an index number. Here's the thing that people don't know. On any type of root, square root, cube root, quartic root, or whatever, the index number, the number in the tail, is actually the most important number. This number right here is the most important number. That's the number you should look at first, is this one, not the big number on the inside. That's a misconception people have. You need to look at this one. This one will tell you how to solve that problem, how to simplify it down to its final answer. It'll explain why are you getting the answer you're getting. This number will tell you that. Okay? Then the number on the inside is called the radicand. This is the number we're going to try to break down. We're going to try to simplify it. Now most radicals or roots in this case, most of them are usually decimals. They're actually called irrational numbers. But some aren't. Some are very, very nice, clean numbers, and that's what we're going to talk about today. Okay, but those are the vocab words I want you to know. So if you have a root, these are the numbers, or these are the words I'll start using a lot in here. So when you hear me use index number, you should know what to look at. If I say radicand, you know what number to look at. So I'm going to use them over and over and over. So get used to that, okay? Remember, the symbol is called the radical sign, not a square root symbol. So get used to that. Okay, now, the goal today, when we start simplifying these, is we're gonna do a couple examples. I have like 3 numbers picked up that I wanna do. We have to find what they call, quote unquote, this principal square root. That's the answer I'm looking for on certain problems. Okay, principal square root. It's also known as simplest radical form. Those are words that we'll use, and we'll look at that one tomorrow. I'll put that on the board tomorrow. But we're gonna try to find the principal square root. This is the answers for these types of problems, without typing in the calculator. All right, so let's do an example here. Okay, here we go. Let's say I give you a radical here. So I'm gonna give you a radical sign, and I'm gonna put a 64 on the inside. Okay? Now, when you see this, there is a radical sign. You can see it, the little house with a little tail. They do have a radicand. That's the 64. That's the radicand number, the number on the inside. And there is, and I know this seems weird, there is a number out front. It would be in the tail. A little number out front. The number that's in the tail, since they don't have one printed, like it's not given to you, this is the one time in math, I know this is going to seem a little weird, it's actually a 2. It's actually a 2. It's the only time in math you can assume you have a 2 on a problem. Because usually, like in algebra, like when you had variables, let's say like in algebra you had like a variable x. What's the power on the x? 1, and what's the number out front? 1. You could always assume that. That's like the thing in algebra. You can assume there's 1s everywhere. But in like pre-calc geometry in algebra 2, when you have radicals, it's a 2 sitting there. It's the only time in math we assume 2s, which is a weird thing. Like, why wouldn't it be a 1? What does it mean? Like, what is this? Oh, this is a radical sign, and it has an index of 2. This is actually called a square root. It's called a square root. Now, let me explain like where the name comes from. What this problem is actually based on, it's based on this problem right here. That's where it comes from. Okay. How you'd actually say this problem out loud, the actual problem that would give you this as an answer, this is called x squared is equal to 64. Right? That's how you say that problem out loud, right? That's the verbal expression for that. So when you solve this problem, right, you have to get the x by itself, so you have to get rid of any of the numbers. You have to do an inverse operation to the other side. You have to do an opposite, right? That's what we learned in algebra class. You either add or subtract, you would divide or multiply, but when there's powers, the inverse operation, when you take it to the other side, is a radical sign. And so when you take this over to the other side, the power 2, right? You're going to have the power 2, you're going to take it over, you'll put a square root on the 64, because this power 2 actually sits right there. Does that make sense, why they call it a square root now? It literally has the word square in it from the original problem, so they call it a square root. That's where the name comes from. Okay, now, most people know how to find answers for these, but I want to explain it in case you don't. You could type it in the calculator and it would give you the right answer, or at least this one has a nice number, but some of them would give you a decimal across the screen, which we'll see here in a minute. But what this means, the square root of 64, square root of 64, means the first thing you should look at is the index number. Index number is the important number, right? That's the little 2 sitting there because it's square, right? Square root. This number tells you that how you get your answer for the square root of 64 is that there is 2 numbers, 2, that you multiply on that you multiply together, that you multiply on itself, that would give you 64. 2 numbers multiply to give you 64. That's what the little index number is telling you. So what number do you multiply on itself? 8. That's your answer, right? That is the answer I'm looking for. This answer is called the principal square root. It's called the principal square root. It's 8. Now there's another answer as well. There's another answer that could work for 64. Negative 8. Negative 8 would have worked as well. But the principal square root is the positive answer. But there is 2. You're looking for a number that you can multiply on itself, because there's 2 numbers that multiply and give you the 64. And that's what they're doing. They're trying to figure out the one number you multiply on itself that would give you the 64 on the inside, since there's 2. Okay? Does that make sense what a square root is? So if you were to actually type that in the calculator, it would tell you 8. That's all it would tell you. Question?
Could you you have a negative number for the index number?
Negatives, yeah, technically you could put a negative number on the outside. That's something we would look at in like algebra 2. They'd show you, all it does is make fractions, that's what it does. But, I know it's weird, but you could put a negative on the outside, not on the inside though. The inside you can't put negatives on. I'll explain that later, that'll be tomorrow's kind of explanation. Okay, makes sense about the square root idea? Like how you do it? Let's do another one, exact same thing, because again, I only have 3 numbers picked out that I want to try. 64 is one of them. So let's look at another one. Let's look at one that you don't know the answer to. Square root, like the radical sign with the index number 2, well, the square root of 12 without a calculator. Okay? So you're thinking, well, that's not possible. Which I agree, because what's my index number? 2, right? It's 2, so I'm looking for 2 numbers that multiply together that would give me 12. So you're thinking of every combination, you're thinking, okay, 1 and 12, 2 and 6, 3 and 4, none of them are working. Okay, it'd be like 3 point something, right? It's 3 blah blah blah. Okay, it's a weird number. It's just a weird, crazy number. It's like 3.4 or something like that, right? That number, the answer for this problem, if you were to try to type it in the calculator, it would give you this crazy decimal across your screen because your answer is irrational. It's an irrational number. Now, if you don't know what the definition of irrational means, it means that the decimal you're going to get never ends and it never repeats. In fact, a perfect example of an irrational number is pi. Pi is irrational. Okay? The number doesn't repeat and it never ends. Now, I'm not saying that the answer for the square root of 12 is pi. It's not. It's 3.4 or something. Did you type it in, Brandon? What did you get? Was it 3.4?
Around about 3.4 to 3.5.
Okay, so we're in that ballpark. There's a ton of decimals across the screen, right? Now, the reason why I know it's irrational, because there was no number. I listed up all the numbers that multiply to give me 12. I could never find one that was just the same number that multiplied together. So it had to be a weird, crazy decimal. Okay? All right, now, I said there's a way to do this problem to get the exact answer without a calculator. There is a way. Because the calculator gives me a decimal approximation. Brandon even said it was like between 3.4 and 3.5. It approximated. It didn't know it. So here's how you do it. Give me any 2 numbers that multiply to give me 12. 3 and 4. Good choice. Okay? 3 times 4. You agree 3 times 4 gives you 12. Okay? We can break those numbers down further. Now, the number 3 you can, just 1 and 3. I'll ignore the number 1. But how do you break down 4? 2 and 2. Okay. 2 times 2. So these are all the numbers breaking down 12 as far as you can. I can't go any further. What I mean by breaking down, you're trying to go down to prime numbers without using the number 1, because 1 goes into everything. So that I can't go any further. The 2s and 3s don't break up any further. Remember, prime numbers are 2, 3, 5, 7, 11, 13. Those are prime numbers, right? You're trying to break it down as far as you can, whatever your number is. You get down to this point. Here's how you get your exact answer for this problem without a calculator. What's my index number?
2.
2. So what this means, I'm looking on the inside of the radical sign, right? I'm looking for any pair of numbers that match. Is there a pair of 2 numbers on the inside that match? 2 and 2, right? You agree, this is a pair of numbers. It's a pair, there's 2 of them. That's what the index number tells me. I'm looking for 2 numbers that match. I did find 2 of them. So what you're gonna do is you cross one out, you kick one out. That's how it always works. You cross one out, kick one out when you find your pair. So this 2, the big 2 goes to the outside. That one disappeared because you crossed it out, and the 3 was left over, and I didn't circle the 3 and I didn't kick it out. So the 3 is still under the radical sign. This is the exact answer for the square root of 12. It's the answer I'm looking for when I want the square root of 12. It's actually called the simplest radical form, the principal square root, whatever you want to call it. Okay, I call it the simplest radical form. That's the correct term for it. You simplified it. Now, some people will look at it and go, okay, yeah, where do I kind of get it? I see that you look for a pair and you kick one out, but how would you do it if it was a different type of radical? So let's do one of those. So, this is my last example for radicals, and then we'll do a bunch tomorrow, and I'll have you practice over and over and over until you get really good at it. So, the cube root, so now we're going to do a cube root now, not just a square root, a cube root. They have to print the number in there. If it's anything other than a 2, they have to put the number there, the index number, because 2s are the only number you can assume. Let's put a 16 here. cube root of 16. So, what's the first number you should be looking at?
3.
Index number, the 3, okay? So what we're trying to figure out is 3 numbers that would multiply together that would give me a 16. Well, it's not possible. Think about it this way. 2 times 2 times 2 gives me 8. Doesn't work. 3 times 3 times 3 gives me 27. So it's between 2 and 3. So that's a weird, crazy decimal. Okay? So I need the exact answer because this is obviously going to be irrational. So I want the exact answer. So here's how you do it. What are 2 numbers that multiply to give you 16?
4, 4.
4 and 4. Okay, that's what most people always pick. 4 and 4. Break those up even further.
2, 2.
2s and 2s. Okay? So 2 and 2, and then this one over here breaks up to 2 and 2. Right? Broke it down. I can't break those up any further without using 1s, and I want to ignore 1s. Okay? Now, we're down to the point where I broke down the number as far as you can. Now what we're looking for is a triplet of numbers. 3 numbers now, not 2 like the last one. We're looking for a triplet of numbers. We have 3 2s. We have a triplet of 2s that are in there, inside the Radical House anywhere. They could be organized any which way. But I did find 3 2s in there. I'm finding a triplet. So how you do this? You cross them out, you kick one out. You always kick one of the triplet out. If it was 4, like a 4th root, you kick one of them out, you cross all the rest out. Now, do you agree that I didn't circle one of the 2s?
Yes.
That's still under the Radical House. Because I'm circling the triplets. So one of the triplets gets kicked out, and the only thing that's left is the 2. That's how you do it. Question?
If you were to do a 4 for the index number,
Yeah.
would you try and find quadruplet?
Yeah, so I tried to find a quad. So in fact, the answer, if I was trying to find a 4th root, the answer would just be 2. Because I'm looking for 4 numbers that match, and I kick one out. There's nothing left on the inside, so it'd just be the answer 2. So we'll look at those tomorrow. That's what we'll look at. So the goal today, what I'm showing you here, is my personal shortcut for how to do this as fast as you can. I personally believe this is the fastest way you can do radicals. Fastest way, without a calculator. It's way quick. Like, me explaining it is taking way more time than I would ever do on a piece of paper. Because I get so used to the powers of 3s and 2s, I can just look for triples and doubles and kick them out. Okay, let's get to our last slide here. Because, and again, we're going to come back to this. Don't think like I'm one and done. No, we're going to do a ton of different radicals tomorrow. That's the whole goal. Can you get good at this? Because when we get into right triangles, this is where it comes to life. Like, this is why we have this. Because I know a lot of time people always ask, like, Ward, when are we going to do this? Like, when would I use this in life? It would be used in the right triangle situation. Like construction, it would be used in some type of fabrication, or you have triangles that are involved. I know that seems silly, but there is. Triangles the most structurally sound object we have. So if you're constructing stuff like bridges and road construction, or you're building A-frames in houses, it's using right triangles. So that's where radicals would come in, that's why they have calculators with those radical signs on them. Okay. All right, we'll get to it. That'll be tomorrow. Today was just to introduce it. Last property today, this is technically my last slide. I want to talk about one theorem. One theorem today, here it is, 8.1. It does not have a name, but I like it right down. So the altitude is drawn towards the hypotenuse of a right triangle. Then the 2 triangles that are formed are similar to the original and each other. Now again, I'm putting all the page numbers here because we did jump out of chapter 4 and we went to chapter 8 for a little bit here. So
Altitude.
that's one of our vocab words. So we're going to talk about that. It's a line that you're going to draw in a picture, and we'll talk about it here in a second. I'll let you write this all down. But again, we're drawing a new line, which Kevin asked, what's an altitude? That's one of our new lines. It's one of our new vocab words we have to talk about. So we have a right triangle, we have a hypotenuse, we're going to draw a line and altitude towards it. It'll form 2 triangles on the inside of the picture, and those triangles are similar to the original and each other. Now again, I'll give you the picture here in a minute. That'll hopefully explain this to you. And then we'll talk about what the word similar is, which you can kind of see my definitions sitting there. This is my last slide today. Remember, the word similar, I want the triangles to be similar, means if you go back, they have to be proportional. The one postulate we have up to this point, for things to be similar to each other, they have to share 2 angles. That's all it takes. again, I'm putting page numbers because we're in chapter 4 still, but I'm mixing some of the sections from chapter 8. That's why the page numbers are so wonky and weird.
Are we doing that scrimmage again today?
Yeah.
Are you just pressing again?
Probably. Might have you play some defense against our offenses.
Yeah.
Were you there yesterday?
I was gone. I had family coming yesterday.
Did you record it?
No.
Oh.
You might have it. You might have us recorded today. Alright,
Is she
here we
gonna
go.
be there today, though? Are you gonna be there today?
Yeah, I'll be there. So, alright, I'll be late, but I'll be there. Alright, here we go. This is the picture they're talking about. Now, what an altitude is, because Kevin asked, what's an altitude? An altitude is a line you draw in any picture you want, but you go from the highest point of your picture down to the bottom, straight down. It's like an altitude of an airplane. They drop a line directly from where the airplane's at in the air, straight down to the ground directly below it. That's how tall the airplane is, like how high it's off the ground, I should say.
Wait,
Right.
So
The idea is on this picture is that they're giving you a right triangle. Now I'm gonna redraw this because I have the picture already broken up for you. But this is the right triangle that they're giving you. This is A, this is C, and this is B. And the right angle is right here. Okay, that's the big triangle, that's this one. Now most people, if I ever asked you to draw a right triangle, they'd probably never draw the right triangle like that. They always draw it like up and down, it doesn't matter. And altitude is drawing the line straight down from there. That's the height of the triangle. Okay? It's how tall it is. Well, that's what they did. Now, do you see when they draw that line straight down, it makes the right angle. That's what an altitude is, by definition. But do you see that it broke this thing up into two different triangles, the two smaller ones? Do you see that now? These are the two small ones from the original. It's this one and this one. Okay, from the original. Okay, what they're saying on this theorem is that they're all related to each other. The small and that really tiny one, BCD, is related to ACD, which is related to the big one, ABC. They're all related. They're all perfect scales. It's like if you were to take your phone and take a picture of these, you could zoom, like turn it and zoom, and it would make this one. And then you could zoom this one, and it would make the bigger one. Like they're all perfectly related to each other. There's perfect scales image. The walls would actually match perfectly. The reason being is that they share two angles. That's why. And I'll show you why they share two angles here in a second. That would be the whole reason why this works. Question?
On technically CDB, it looks exactly the same as the smaller CDB.
Yeah, this one is supposed to be that one. Yeah. So what I did is I just took these and I broke them up and made it down here so you can see them. Yeah. All right. So let's explain. Why does this little tiny triangle, which is this one, why is this related to the big one? Okay. Well, here's why. Do you agree that the big triangle has a right angle in it? Okay. So does the small one, right? The small one does have a right angle. It's right here. So there's one angle that matches. And on the big triangle, do you agree that the big triangle has angle B on it? Has angle B? The small one has angle B. So it does share two different angles. They share the same two angles, so boom, they're automatically perfect scales of each other. So there exists a number I can multiply on this wall, and it would make the bigger wall on the other triangle. Okay? And this triangle over here is also related to the big one. Because, so this triangle right here is this one. Do you agree it has a right angle, like the big triangle does? And the big triangle has angle A, well so does this one, has angle A. So this little piece, which is this guy right here, this one is related to the big triangle. So I could turn it and zoom and it would make the bigger one. So they're perfect scales. Again, similar means that they're proportional. So they're scales of each other. They're perfectly scaled up. All right, questions at all about the property today? Okay, we only got about 5-6 minutes left here, but homework due tomorrow are these. Remember, on these first four, you can do flow charts. These last ones, you're finding like X's and Y's and telling me which parts are equal. This is easy. This part, take your time on. Especially if you're doing a flow chart. Okay, but there you go. That's your notes for today. Pretty easy.
Can we go back to that?